Oliver Edtmair from Berkeley. So he will speak about 3D convex contact forms and the Ruelle invariant.
Okay, great. Well, thanks a lot for the invitation. I'm going to talk about convex contact forms and the Ruelle invariant, and that's all based on joint work with Julian. Okay, so let's consider R2n and equip it with the standard symplectic form and the radial Ruelle vector field and the induced Ruelle form lambda. Now, by a star-shaped hypersurface, I mean a hypersurface that is transverse to the radial vector field. And if we take such a hypersurface Y, then the restriction of the Ruelle 1 form, the hypersurface, is a contact form. So associated with it has a rate flow, which is a very interesting object to study. So the simplest example of a star-shaped hypersurface is just the round unit sphere. The contact structure I get on that is called the standard contact structure. And so it turns out that, in fact, as a contact manifold, any star-shaped hypersurface is isomorphic to this standard sphere. So I can think about a star-shaped hypersurface as defining a contact form on the standard sphere. And conversely, every contact form arises this way. So an interesting special case of a star-shaped hypersurface is a convex hypersurface. They have many special dynamical properties, both proven and conjectured. And so here's an example of a very interesting conjecture about them. That's Viterbo's conjecture. And it says that if I have a convex hypersurface, then the systolic ratio is less than or equal to 1. So here the systolic ratio is the minimal period of an orbit, and it's normalized in such a way that it's invariant under scaling and equal to 1 for the round sphere. And in this conjecture, convexity really is an important assumption. So in fact, there's a theorem by Abundandlu, Bramham, Renievich, and Salomo that says that there exist star-shaped hypersurfaces with arbitrarily large systolic ratio. So convexity is important here. But from the point of view of symplectic geometry, this convexity assumption is maybe slightly mysterious because it is not preserved by symplectomorphisms of R2n, but the rate dynamics is. From now on, I will go to dimension 3. In the very end, I will speculate a bit about high dimension, but now we are in dimension 3, and I make the definition, the following definition. I call a contact form on the standard free sphere a convex if it arises from some convex hypersurface. An interesting problem would be to try to formulate some intrinsic notion of convexity that does not reference an embedding into R4. And in fact, there exists a very useful such intrinsic notion of convexity. So that's due to Hofer, Wysotsky, and Zehnder. It is called dynamical convexity. So we call a contact form on the standard free sphere dynamically convex if every Rabe orbit, every closed orbit, has Conley-Zehnder index at least 3. So maybe it's not immediately evident why this is so useful and what it has to do with convexity. But it turns out that if I take a hypersurface and assume that the curvature is strictly positive, so that's slightly stronger than convexity, then that implies dynamical convexity. So there are convex hypersurfaces which are not dynamically convex, but whenever I have strictly positive curvature, then I have dynamical convexity. And also it turns out that this condition on the Conley-Zehnder index is very useful if I try to prove things by holomorphic curves in symplectization. That's a very useful notion. Now, a natural question I can ask, and in fact has been asked, is whether every dynamically convex contact form is also convex. And so here is one reason why one might find this question so interesting. So there's a theorem, again, by Abundandlu, Bramham, Renievich, and Salomo, that says that there exist dynamically convex contact forms whose systolic ratio is arbitrarily close to 2. So this illustrated the situation in a diagram. So we have dynamically convex contact forms and convex ones. So there's the non-strictly positively curved ones that are kind of outside of the dynamically convex region, but most convex ones are dynamically convex. And then we have this ABHS contact form. Now there are two options. Well, either this contact form is in fact convex. In that case, it would be a counterexample, the Wiederpost conjecture, which would say that the systolic ratio has to be less than 1. Or it is the first example of a dynamically convex contact form that is not convex. But the annoying thing is we don't know which of the two options is true. And I don't know either. But so what is the main theorem of my talk here is the red dot in the diagram. So I can prove that there exists a dynamically convex contact form that is not convex. So I don't make a statement about this special ABHS contact form, but I can define some other contact form. Right, so now that's the first example of a dynamically convex one that is not convex. Okay, so the kind of main ingredient of our proof that can distinguish convex contact forms from dynamically convex ones is the Ruelle invariant. So that takes a contact form on the standard free sphere and it associates to the real number, and this real number measures some average measure of how much the rate flow of the contact form rotates. So we'll say a bit more about how that invariant is defined in a minute. But now there are two main steps to the proof of the existence of dynamically convex contact forms that are non-convex. So the first step is we can prove that, so we take this Ruelle invariant and we normalize it by volume, such that it is invariant under scaling. And now we can prove that there is some strictly positive constant C, such that for every convex contact form, this normalized Ruelle invariant is bigger than that. So there's a strictly positive uniform lower bound. And on the other hand, we can prove that there exist dynamically convex contact forms such that the Ruelle invariant is positive but arbitrarily small. And so putting these two things together, we see there are dynamically convex contact forms that are not convex. Okay, so here's a brief overview of how to define the Ruelle invariant. So we take a contact form, alpha, and the Ruelle invariant is defined to be the integral of some rotation density, rot, with respect to the contact volume form. Now this rotation density is defined as follows. So I pick a point P in the free sphere. Step one is to choose a non-zero vector in the contact plane at that point. Now with the rate flow, I can transport that along the rate trajectory through the points. I get a vector field along that trajectory. If I now also choose a trivialization of my contact structure, I can view this vector field along the rate trajectory as a path in R2 minus the origin. Right, and such a path has a well-defined rotation angle. So I measure how much the angle changes with respect to time equal to 0. Right, so rho equal to 1 means 1 full rotation here. And then finally, I can set the rotation density at the point P to be equal to the limit as the time goes to infinity of the rotation number rho of t over t. The mean number of rotations per time unit for a very large time. So it is a consequence of the ergodic theorem that this actually is well defined almost everywhere and also integrable. So we can and finally integrate it to get the Ruelle invariant. So this rotation angle function rho that does depend on the choice of trivialization, of course, and also on the choice of vector v. But if I take this long time limit, then this dependence disappears. So in the end, the Ruelle invariant is independent of choices. Okay, so now let me talk a little bit about how to get a lower bound on the Ruelle invariant for convex contact forms. So our estimates are based on this formula here, which relates the rotation of the linearized rate flow to extrinsic curvature quantities of the hypersurface. And I was told that this formula is originally due to Ragazzo and Salomao. So what are the ingredients here? First of all, we have the rotation angle function. That's the one that appeared in the definition of the Ruelle invariant. And here I measure with respect to a very specific trivialization called the quaternionic trivialization. So it turns out to be useful to identify R4 with the quaternions. Also have new the unit normal vector field showing up, and most importantly, the second fundamental form of the hypersurface. Right, so I can now express how this angle function rho changes along a trajectory in terms of the curvature of my hypersurface. Okay, so a rather easy consequence of this formula is the following. If the hypersurface y is convex, then the second fundamental form is positive semi-definite. Now, that means that both of the curvature terms in this formula are non-negative, and that implies that the derivative of rho is non-negative. And then if you look at the definition of the Ruelle invariant, that defines that this Ruelle invariant is non-negative. So in other words, if I have a convex hypersurface and have this special trivialization, then at every single point, the linearized rate flow must rotate non-negatively, always in positive direction. But of course, we want to have a bit more, right? We want to have a strictly positive lower bound, and we also want it to be uniform among all convex hypersurfaces. And so the first step of our estimates is this inequality here. So we can prove that that follows rather directly from this curvature rotation formula and the definition of the Ruelle invariant. We can prove a lower bound in terms of the integral over y of this curvature quantity, sectional curvature. The second fundamental form in the direction of I nu. And then from this point, we look at this curvature integral and then keep doing estimates. And in the end, I claim one can get a strictly positive uniform lower bound. Okay, so that's what I want to say about the lower bound for now. Let me now come to the construction part. So I recall that we want to have a dynamically convex contact form with very small Ruelle invariants, such that it violates the bound for convex contact forms. And here we use a variant of a construction due to abundant Brahman linearity and Salomon. So that's an open book construction. So we take a Hamiltonian diffeomorphism of the disk, or rather an element of the universal cover. And then we can perform an open book construction to get a contact form on the standard free sphere. And so the rate flow of that will have the disk as a surface of section and phi as the Poincare return map. An easy example is if phi is a rotation. So in that case, we would get something that is strictly contactomorphic to an ellipsoid boundary. Okay, so now we want to produce something that has small Ruelle invariant. And the intuition here is that if I look at my Hamiltonian flow in the disk, and if it rotates counterclockwise, that's going to increase the Ruelle invariant. And if it rotates clockwise, that's going to decrease it. So if we want to make the Ruelle invariant small, we have to introduce some clockwise rotation. But we also want to have dynamical convexity, and that's a bit of an opposing condition because it says that we have to have a lower bound on the Cohn-Lysander index for periodic orbits, and I can rephrase that as a lower bound on the rotation angle. If I follow a periodic orbit, then I have the linearized wave flow along that, and I can rephrase the lower Cohn-Lysander bound as a lower bound on the rotation angle. So that means if our Hamiltonian flow on a disk has too much clockwise rotation in it, then we risk producing periodic points where the Cohn-Lysander bound is violated. So we have these two opposing conditions, and now we have to try to make a compromise. And so here is I have a picture of how this can be done. So we start with a disk, we divide it into sectors. So in this picture, we have 4 sectors. And then my Hamiltonian diffeomorphism is going to be the composition of 2 diffeomorphisms. So the first one, phi h, that is a rotation. So we do one full rotation, and then we do one more sector. So here with 4 sectors, we have 360 plus 90 degrees. So if we stopped here, we would have an ellipsoid boundary, and that is, of course, it is dynamically convex, but it also has big Ruelle invariant. And so now we have to produce some clockwise rotation, and that's what phi g does. So here we draw a whole lot of small disks inside our big disk. And inside the small disks, we start rotating in clockwise direction. So ideally, we would want to rotate as far clockwise as possible to get the Ruelle invariant down. But there's a limit to that because we will have periodic orbits on the centers of the small disks. And if we rotate too much clockwise, then we get too small a Convex-Center index. And it turns out that kind of the maximum I can do is slightly less than 2 clockwise rotations. After that, I destroy dynamical convexity. Right, so there's now a couple of more parameters I can modify. So first of all, I can change number of sectors. Here I have 4. I can make that larger. I can change the sizes of my small disks. And it turns out if we make the number of sectors very, very large, and also the small disks very, very small, and if in addition guarantee that the small disks cover a very large fraction of the area of the big disk, then I get a very small Ruelle invariant. So that is the construction part. Right, so that's what I wanted to say about the second part of the proof. And let me finish my talk with a slide on kind of very direct further questions that we're trying to think about now. So the first one, of course, one can ask whether it's possible to play this similar game in higher dimension. So here I was talking about dimension 3, but of course, dynamical convexity also makes sense in higher dimension. So can I prove a similar theorem here? Then a second question one can ask is, what is an optimal lower bound on the normalized Ruelle invariant for convex hypersurfaces? So one reason why this could be interesting is that we still have this ABHS contact form, which is dynamically convex with a systolic ratio roughly 2. And right now we cannot really say anything about that because the constant C we have so far, I mean, we didn't really try to make that. We prove that it's positive. I guess if one goes through all the estimates, one could get some explicit number, but right now that number would be very small. So it's of no use so far to prove that this ABHS contact form is not convex. But maybe if one understands the estimates a bit better and then can get a higher lower bound, then, well, maybe it could prove that this is not convex. Maybe it also does not work, I don't know. But that's an interesting thing to think about. Yeah, so that's what I wanted to say. Thanks a lot for listening.
Thank you very much. Thanks very much, Oliver. So, of course, ask questions if there are any.
Can I ask a question?
Yes.
Is the Ruelle invariance different from the average Convex-Center index?
So what is the average Convex-Center index?
Well, if you trivialize the bundle, you can, on each piece of orbit, say what's the Convex-Center index along this piece of orbit. And it should be in 2 dimension, I mean, or 3 dimension, it should be just a rotation on the plane, on the contact plane. And then again, by the usual argument of ergodic theory, you can, I mean, you can go to the limit as the length of the orbit goes to infinity, and then do the average over your manifold, over your sphere here.
Okay.
And that, it seems to me that this is the same as the Ruelle invariant. I may be wrong. But in any case, it would be a natural candidate in higher dimensions.
Okay, okay. So yeah, I haven't seen the definition of this mean Convex-Center index, but it sounds like it's a similar thing.
I think it should even maybe be the same. And then the theorem you mentioned by Salmau and, sorry, I forgot the name, but anyway, should tell you that on a convex set, you have to rotate a little bit faster than what the formal convexity gives, I mean, than dynamically convex.
Mm-hmm.
So somehow there's a minimal speed that is that is a little bit bigger than what it gives, and then you would have that you would have a similar. Well, of course, you have to make your construction as you did with the disk in high dimension, which is maybe not so easy, but I don't know.
Oh yeah, we will think about that. Thanks.
Thanks, very nice.
Can I ask a question?
Yes.
You may know that I don't remember very well, but there was this recent work of Ginsburg and Maccarini in higher dimensions. So I don't remember. Do they assume symmetry? I thought they proved something like convexity implies dynamical convexity. I'm just curious how this is related, if you know it.
I don't know about the existence of that paper recently. I haven't fully read it. But yeah, it seems they have...
To be clear, I think. Symmetry, something like that.
Yeah, so there definitely is an assumption that we have some symmetry group acting on the hypersurface. And I think they prove something like, they have also some notion of dynamical convexity, and they prove that there exists something that is not dynamically convex. It is dynamically convex, but not convex, but it is really with some symmetries going on. It does not imply this general case here.
Okay, thanks.
Can I ask a question?
Yes.
Okay. But first of all, maybe an answer to Claude. Yeah. The Ruelle invariant is actually the integral of the average Conley-Zender index over the whole thing. Yeah. And yeah. This result.
Michael just posted that it's true up to a factor which is 2. He says
up to a factor. Yeah, exactly. Because it's just that Ruelle defined this a long time ago. I think before Conley-Zender paper.
Oh, absolutely.
Yeah. But not for. He was actually not considering, I think, on energy levels. He defined it maybe first for say Hamiltonian systems on R2n, and then the invariant of an invariant measure, things like this. Yeah, in slightly different settings. And yeah, this I think what Victor and Leonardo proved was that they have examples of dynamically convex things which are not, which have a Z2 symmetry, and they are not symplectomorphic to something which is convex through a symplectomorphism which preserves the symmetry. So, but this does not exclude that they are symplectomorphic to something convex, but destroying the symmetry. So in some sense, it doesn't answer the question as you do. And then, to the question, what do they want to ask? Yeah, I forgot. It was a good question.
In the meantime, I can ask a bad question.
Ask another question and then come back.
You said that some convex are not dynamically convex. Is this because they are degenerate? It's a degenerate situation?
Yes.
Degenerate?
The polydisk, then I think
that's just because of the degeneracy.
Yes.
So, okay, that was. Now I asked the bad question. Alberto remembers his good question. Maybe.
Yes. No. Well, not that good after all, but say it's a question at least. So, well, if I understood well with these examples, you can make, so you have dynamically convex things with arbitrary small Ruelle invariant, right? Also when normalized by volume, right? Is it clear that dynamically convex implies that the Ruelle invariant has to be positive?
No, I was wondering about that as well. So it seems if I take this specific construction as a starting point, I could not get below 0, but I do not know. That's a good question.
Couldn't it follow from these the things of Michael with the Ruelle appearing as a higher order term in the asymptotics of ECH?
Well, that would be a very interesting thing to think about. Yeah, haven't thought about it yet.
I guess if periodic orbits are dense, then it's true, of course.
Yeah, yeah.
So that's.
Yeah, so generically it will be true, but
well, the Ruelle invariant has some continuity property, and then there's this theorem of Fourier that you could perturb the contact form and make the orbits dense. Although I guess it's not obvious that that would preserve dynamical convexity. That's very subtle. I had a different question. So you asked, what is the optimal constant for Ruelle over square root of volume? So the smallest I can think of is for a cube, where it's like square root of 2, depending on your convention. So do you think a cube could be optimal for that constant?
It is also the smallest value I found. I don't know. It would be cool, but I wouldn't know how to get how to prove that at this point.
Sorry, just a small thing. If you knew it was the periodic orbits were dense, just because it could take a long time, maybe would you not need more? Maybe like the full measure, or maybe not. Yeah. Anyway.
So if we try to prove that dynamical convexity implies non-negative Ruelle invariant, yeah. I don't know. I haven't thought about that.
The orbits could be periodic orbits could be very long, so maybe, but I don't know. Anyway, thanks for the talk. Very nice. Thank you. Very nice results.
So thank you very much, Oliver. And we still have a few minutes maybe for questions if there are more.
And maybe to complete what Barney was saying, then the mean the average Conley-Zender index is also extremely discontinuous. So even if you control it on periodic orbits, you still have problems. If you have many periodic orbits which turn positive.
Okay, so thank you very much again, Oliver.